Good afternoon, everybody. I'm Silvia Salvatore, and today I will be talking about the jet contribution to the gamma ray flux detected in NGC 1068. So my talk will not be about neutrinos, but why are neutrinos important for this source? First of all, in our model, we describe NGC 1068 as a two zones source. And this is done for observational reasons, as you can see on the left-hand side of the slide, where we have an inner corona and a starburst string, which is on scales of 1.3 kiloparsec from the black hole. And then, because if you look at the right-hand side of the slide, you can observe how between 100 GeV and 10 TeV energies, we have a very significant difference in the order of magnitude between the fluxes of the neutrinos detected by IceCube and the gamma ray detected by Fermi. So this cannot be possibly explained by one single zone. So what we do is to fit all this wide range of energies from the radio range to the gamma ray range, and we use this AGN corona, which is represented in this best fit in the slide with every line which is in red, and the starburst ring. And Lx of the order of 10 to the 43 ergs per second is the X-ray luminosity used to model the background photon field for the corona, while 10 to the 40.92 ergs per second is the integrated gamma ray luminosity in the range detected by Fermi-LAT. What I'm doing in my work is to try and introduce a third component, which is the so-called jet. And to do so, I'm constraining it using this radio data by Gallimore et al. In 2004 and Nishiyama in 2022. I'm using these three blobs, the first one at 21 parsec from the core, the second one at 43 parsec, and the third one, which is the head of the jet, at 670 parsec from the core. In particular, if we zoom in the head of the jet, we observe four blobs. So in my calculations from now on, I will be focusing on one of those with radius of 5 parsec, and when I have to account for the luminosity, I will multiply by 4. So we use this radio data to constrain the jet in order to say, okay, is it possible to predict gamma rays by this jet or not? But this is kind of the problem. These are my radio data. So as you can see, below 10 to the 10 hertz, we have this kind of hard spectrum behavior, but for higher frequencies, we observe this, in particular, nuclear emission, which is a very hard spectrum. So soft spectrum against hard spectrum at different frequencies. And what I mean by nuclear emission in particular is a radio emission which can comprehend the first blob plus the second blob plus some other nuclear regions within a scale of 40-50 parsec from the core. So my goal will be to reproduce with this jet those Fermi gamma ray data. And in order to do that, I have to account either for inverse Compton processes or p-gamma interactions. Before starting with those, I have to take into account which is the dominant target field to consider. As you can see in this slide, the corona plus disk environment has an energy density which is way higher than the torus infrared field, even for distances of the order of hundreds of parsecs. So this will be between the two, the one that I will be accounting for. But I also have to account for the synchrotron photon field. So in order to decide which of the two is the dominant one, I can just equate those two expressions there. But this will lead me to need synchrotron luminosities for the three distances of the order of 10 to the 43 ergs per second. And in all three cases, these exceed the threshold set by the power of the jet, which is 10 to the 43 ergs per second. So from now on, I will be considered just the corona plus this target field to be the dominant one for these interactions. So what I do is use this formula here, which considers the Thomson regime, so no absorption processes are taken into account. URAD is the energy density of the radiation field, which is the corona field. UB is the energy density of the magnetic field. And in order to compute it, I need to have some sort of estimate on the magnetic field at those different distances from the black hole where the blobs are. To do that, I use this formula here for the equipartition argument. And this is the final expression defining the magnetic field in those three regions. By plugging that into the inverse Compton formula above, that's what I get. And what I do is equating it to the value that I would need to reach the Fermi-LAT data points, which is 10 to the 40.92 ergs per second. And those are the synchrotron luminosities I would need at 21, 43, and 670 parsec from the core. Now, if I compare the first and the third one with the observational data that we have here and that I plotted on the right-hand side of the slide, we have that these exceed the observational data. The only value which is below the upper limit set by observational data is the one at 43 parsec. But again, we need to take into account that in this case, we're considering a behavior that is decreasing with frequency, while if we look at the whole picture, we don't know actually how this data should be described. What is the actual behavior of the flux with respect to frequency? I forgot also here to mention how there's a very strong impact of the radius of the blob on the final synchrotron luminosity estimate, because it goes to the power of -4. So changing the radius of the blob, even by not even an order of magnitude, can have a very strong impact on the final estimate of the synchrotron luminosity. The other factor that I'm taking into account here is C12, which is used before to compute the magnetic field. But we notice how even by changing nu1 and nu2 that are described there in the expression above, C12 doesn't even change by one order of magnitude, for example, in the case of the second blob. And therefore, C12 over to the power of 4/3 is of the order 10 to the 8, 10 to the 9, regardless. Same goes for the factor K. If we change Q, which is the spectral index of injected cosmic rays, between 2 and 2.5, K ranges between 40 and 300. So again, the dependence on K is not that strong. Another scenario where we could produce these gamma rays is the P-gamma interactions. So here is again another analytical calculation. What we do in the first expression is just the definition of the gamma ray luminosity with respect to the photopion emissivity epsilon, which is given in the expression below. Then what we do is inject a number density of protons as a power law, and we constrain it in such a way that we need the whole power not to exceed the power of the jet, which is what is written in the fourth expression there. And what we end up with is the final expression that you see at the bottom of the slide. But plugging a gamma P max for the protons of 1,000 and plugging P jet, the power of the jet of the order 10 to the 43 ergs per second, even playing with the other parameter, which is QP. We would get gamma ray luminosities, which are of the order of 10 to the 30 ergs per second, so way below the threshold that we want to reach. We also try to ask ourselves, well, what happens if I imagine this blob to be even closer to the corona? Because in in the final expression that you see for the luminosity of the gamma rays, you can see how there's a dependence on d to the -2. So we imagine how by decreasing this d, the final gamma ray luminosity would actually increase. But this has to deal with the fact that for distances lower than tens of parsec, the medium is optically thick. So we wouldn't, even in this case, be able to observe these gamma rays if we consider p gamma interactions. So to conclude, we can say that gamma rays could, in principle, be predicted by this jet component in the leptonic scenario, but we need to take into account the fact that there's a lot of uncertainty on the radio data, and therefore a lot of uncertainty on the emitted luminosity. In particular, we have no idea of how the spectral index is defined. We don't know how to fit those radio data, as I showed before, and we don't have a lot of precision around the radius of these jet blobs. And for example, in a paper published in 2008 by Lenine, they also say that they can predict gamma rays by this jet component. They use a blob radius of 6 parsecs against a radius of 2.7 parsecs, which we use at distances of 43 parsecs from the core, which was my blob number 2, let's say. But very important difference between what we do and what they do is that they account for the background photon field, which is the infrared torus, while in our case, we notice how the dominant background photon field to be accounted for is the one from the corona, because it's dominant even at distances of 100 and kiloparsec scales. So yeah, thank you for listening.
Thank you, Silvia. Other questions?
Thanks for the nice talk. My question might be a very basic question, but why does the jet have this blob structure? Or
I can hear.
Why does the jet have this blob structure? So why does it have the blobs?
These are observational data. Why do I model them as a blob?
Yes, the question was what the physical mechanism.
Yeah, why do you see these blobs? Why is it not like why do you have this patchy image and not like, why is not everything red? Or
that is a nice question. For example, I know that, so for the head of the blob, I would say that there's some sort of bow shock happening. So that's why you notice that. There's also some sort of acceleration mechanism happening for the NE blob, which is the second one, which is why maybe there's like this structure that is noticeable there and not elsewhere. But I'm not very much of an expert around radio data, so I cannot tell you why you see them, where you see them, but we notice this kind of blobs emitted from the core, and just out of simplicity, we model them as a sphere, and everything is homogeneous and symmetrical inside. But there's also a lot of uncertainty on which the radius of this blob would be. Like, should I take into account just the first contour or the third, or this is much more of an astronomer, I would say.
Thank you.
Detail.
Yeah, Walter, maybe you have a comment on that? Different question.
So I actually was wondering about the inverse Compton model. Did you, I mean, you computed this in the Thomson regime. Did you check when the effect of Klein-Nishina suppression would kick in and if it has any impact there?
We studied how this would be, where is it? We actually went through a study who showed how considering the Thomson regime would actually optimize the gamma ray, the synchrotron the gamma ray luminosity emitted in the inverse Compton scenario.
Okay, but I mean, if the cross section is not constant, so if inverse Compton scattering, I mean, the Thomson regime ends somewhere, so you would have like a suppression, right? And so I wondered if that was taken into account, or if you thought about why it is not relevant or something like this. I mean, maybe there's a reason why it's not relevant. If you thought about that.
No, we didn't take this into account.
Yeah, concerning the last question, I'm also not a radio astronomer, but I think this one in the middle panel, you circled this lobe. So this was, I think, the jet interacting, or the outflow interacting with the external medium. Which,
Yeah, the head of the jet.
Yeah.
Yes.
Yeah, so this would be basically a shock developing when the outflow hits the so similar to the models that Enrico was talking about. Yeah? And I guess there's also some uncertainty in the angular resolution here that doesn't allow you really to, it basically sets an upper limit on the radius, but it can actually be smaller than the angular resolution that you have here. That gives you
There's
some
also a lot of problems
uncertainty.
with the with the resolution.
Maybe one quick question. So you talked about C1, 2, and K. Can you maybe you mentioned it earlier? What exactly were these parameters? Is this related to the radio emission, or?
Yeah, this is so nu1 and nu2 would be the boundary of the synchrotron emission, and K is simply the MP to ME ratio to the power of Q minus 1/2. And the dependence on the whole thing would be here in the magnetic field.
Okay. Okay. It looks like that is the result of a long calculation. Okay. Any other question? Then let's thank Silvia again. And everyone in the